Hello students, in this lecture I am going to discuss few applications of the liquid drop model. With the help of liquid drop model we can find out the most stable nuclei. We can find out the most stable nuclei of a isobaric family. So with the help of liquid drop model or whatever formula we have derived in the last class, on the basis of this we can predict, okay, this nuclei will be most stable out of a given family of a isobaric family, isobaric type of family, for which a number, mass number is constant. Second important application is on the basis of the mass parabolas which we can draw with the help of liquid drop model formula. On the basis of that we can predict that either a nuclei is going to emit beta plus particle or beta minus particle. As well as we can find out the Q values associated in this beta emission or beta decay. What will be the Q value in case of beta plus decay or in case of beta minus decay? So first I am going to discuss the mass parabolas for an isobaric family having A equal to odd number. If A is equal to odd number, isobaric family we have, then what type of mass parabola will be formed in that case? I am going to discuss all these things. So first we have to write down the formula. Here, this is the formula we have derived. We have derived in liquid drop model. What is the formula of liquid drop model? Liquid drop model formula is mass of the nuclei, MZA, mass of the nuclei is equal to mass of the constituent particles plus A minus Z mass of neutrons. So this is the mass of constituent particles minus 1 by C square into binding energy. 1 upon C square into binding energy. So basically this is the formula. This formula AV into A minus AS, A to the power 2 by 3 minus AC Z square upon A to the power 1 by 3 minus AA, A minus 2Z whole square, A plus minus delta. Here this is also a function of A, but simply for simplicity I have written it as delta. Here this delta is equal to delta upon A to the power 3 by 4. So even you can write it as delta 1. I can write it as delta 1, and delta 1 here is equal to delta upon A to the power 3 by 4. So for simplicity, in place of writing this complete expression, I am just writing delta 1 here. So here, this is the value of expression of B. But in that case, if you are writing B like this, AV into A minus AS, A to the power 2 by 3, and minus, this will be AC, Z square upon A to the power 1 by 3, minus AA, this will be A minus 2Z whole square upon A, and this will be plus minus delta. If I am writing this type of formula, and this will be delta to the power A to the power 3 by 4, and I have replaced this term by delta 1. If I am writing the expression of B in this form, then all these terms, they will be in terms of, they will have the dimension of energy, so they will be in terms of MeV. Now, if I divide this equation by C square, C square here, and consume this C square, attach this C square with this AV, AS, AC, AA and delta 1, then this will be equivalent to, I can write it as AVA minus AS, A to the power 2 by 3 minus AC Z square upon A to the power 1 by 3 minus AA, A minus 2Z whole square upon A and plus minus delta 1. But here, when I have consumed this or I have associated this C square with this AV, AS, AC, AA and delta 1, then this becomes, all these AV, AS, AC, they will have dimensions of, what is this? This is the, basically this has the dimension of mass. B upon C square has dimension of mass. So now they all will have dimension of mass. They will have dimension of mass, and dimension of mass is AMU. So all these values of AV, AS, AC and AA, it will be in terms of AMU. So I can always write B upon C square equal to this, but you have to remember this, that this AV, AS, AC, AA and this delta 1, all these constant has the dimension, they have the dimension of mass. It means they will be given in terms of AMU. So what I have done here, I have written here in place of 1 upon C square into B, I have replaced this 1 upon C square into B by this expression. So we have find out the expression of the nuclei. These are the masses of the constituent particles, proton and neutron. This is the volume energy term, this is surface energy term, this is Coulomb energy term, asymmetry energy term, and this is pairing energy term. In this pairing energy term, what is important here, outside the bracket we have minus sign, and here this plus sign is for even nuclei, this minus sign is for odd nuclei. What is the meaning of even nuclei? Even nuclei means in a nuclei, if in a nuclei number of protons and number of neutrons both are even number. If number of protons as well as number of neutrons both are even number, then that type of nuclei is known as even nuclei. And the nuclei in which both number of protons and number of neutrons are equal to odd number, then that type of nuclei is known as odd nuclei. Now what we have done here, we have rearranged this equation. This is the equation we have obtained in semi-empirical mass formula in liquid drop model. Now we have rearranged this equation. How we have rearranged? I have joined this ZMP and this ZMN term. I have combined these two terms. ZMP minus ZMN together. So it will become Z times MP minus MN. In various books, you can also find out in place of MP, they are writing it as MH, because one H1 nuclei means one proton. One H1 nuclei means proton. So in many books you will find out that in place of MP, sometimes you will find out that in place of this MP, they have written MH. So we have combined these two terms. Now consider these two terms. This AMN minus AV into A. So I have joined these two terms together, this one and this one. You have combined these two together. A is common here and it will become MN minus AV. So here I have combined these four terms. After this, we have this term, AS a to the power 2 by 3. So here I have AS to the power a to the power 2 by 3 here. This is this term AC Z square upon a to the power 1 by 3, and then minus AA. We have opened this bracket. I have opened this bracket, this A minus 2Z square. So here in denominator we have A, so this term will become A square by A. So here we have A. Second term will be 2Z square. So this will be 4Z square upon A. So this is 4Z square upon A with plus sign, and minus 2 times A into 2Z. So minus 4AZ upon A, this A. So this will become minus 4Z, and this will become plus minus. This plus will become minus, this minus will become plus, because here this minus sign is here. When we will open this bracket, this plus will become minus. So this plus will become minus. So even nuclei is representing for minus. And this minus will become plus. And now this plus is representing for odd nuclei. So sign is changed. Sign is changed here. After this, we have further simplified this equation. What we have done, we have combined all the terms having A together. So we have combined these these two terms together. We have combined these two terms together. How? This is Mn here, minus Av here, minus Av here. This As, if we multiply in numerator and denominator by a to the power 1 by 3, then in numerator you will have a, and in denominator we have a to the power 1 by 3. So we have taken a common, and this will be as upon a to the power 1 by 3. Another term which we are taking, that is here, that is from here. This is a into a. So we will have Mn minus Av minus aa minus as upon a2. So in all these four terms, first term, second term, third term, fourth term, a is common. So we have combined all these four terms. These four terms are combined together. Now we are going to combine these terms. We are going to combine these terms here. Which terms? Having Z. Having Z. So here we have Z times MP minus Mn. If you take minus common, then it will become minus Z MP minus Mn. It will become minus Z MP minus Mn, because mass of the neutron is always greater than mass of proton. So this minus times Mn minus MP into Z is here. This is here, and another term will be minus 4AA, 4AA from here. This is another term. This is another term. So we have combined these two terms with this term. So here this will be minus 4AA into Z. This will be here. After this, we have left with two terms. One is AC Z square upon A. So take Z square common. So AC upon A to the power 1 by 3 is here. And from this, we will have 4AA upon Z. 4AA upon Z upon A into Z square. And last term is delta 1 plus minus delta 1. So in this way, we have simplified the formula obtained in semi-empirical mass formula or in liquid drop model. Now, this bracket term, I represented this bracket term by A, small a. Suppose I assume that this first bracket is equal to A. I'm assuming that this A let A is equal to Mn minus Av minus Aa minus As upon A to the power 1 by 3. We are assuming that this is equal to small a. So I have written this A multiplied by this capital A. So first term will become A into A plus second term, this second bracket I am representing, or I am assuming the second bracket as X. I am assuming that this is equal to X. So I have written this as X equal to minus 4AA minus Mn minus MP. This is equal to X. This is equal to X plus I am assuming this term, this bracket term, third bracket term, I am assuming this bracket term as Y. I am assuming that this bracket term is equal to Y. So this Y is equal to 4 times AA upon A plus AC upon A to the power 1 by 3. So these three bracket terms is assumed as A, X and Y respectively. A, X and Y respectively. So my equation will become, my equation for the mass of the nuclei will become A into A plus XZ plus YZ square plus minus delta. From here, you can find out one thing, that all this A, X, Y and delta, this A, X, Y and delta, they have dimensions of mass. They have dimensions of mass. Dimensions of mass or energy. They have dimensions of mass and energy. So from here you can also find out this is Mn. So the dimensions of this A and M, and they will be equal. Similarly here, this X has the same dimension as this Mn and Mp. Y has the same dimension. From here, I can find out this Z is a number, so dimension of Y will be equal to the dimension of this mass of the nuclei. So all the three terms, A, X and Y, they can be written in terms of dimensions of mass, or sometimes you can write everything. Even you can write this mass in terms of energy units. Then I will write this, in that case, I will write this A, X and Y and delta in terms of energy units. So the dimensions will be same. The dimension of this M, A, X, Y and delta, their dimensions will be same. So in this way, we have simplified the liquid drop model formula into a simple form. Now what we have done, now what we will do, here you can observe this X is independent of A, this A is partially dependent on A, this dependency is through the last term, and here this Y is nearly proportional to 1 upon A. If we assume A as constant, if I assume A is constant, if I assume A as constant and then plot, and then I will plot mass of the nuclei. If I assume A is equal to constant and then plot this mass of the nuclei A, Z as a function of Z, as a function of atomic number. If I plot MAZ as a function of Z, then you will find out, if we plot this as a function of Z, then we will find out, plot like this, we will have a parabola. We will have a plot like parabola. So if we plot this MZA as a function of Z, then we will find a parabola. And this parabola is known as mass parabola. You have to remember this, that here A is a constant. And this type of parabola, this is known as mass parabola. Mass parabola. Here in this parabola, we can observe one thing, that at the lowest point here, at the nuclei which is at the lowest point of this here, the nuclei which is representing the lowest point of this parabola, it will have lowest mass. This will have lowest mass. This nuclei which is present here at the lowest point of parabola, this will have the lowest mass in this isobaric family. In this isobaric family, basically this nuclei will have the lowest mass. What is the meaning of lowest mass? What is the meaning of lowest mass? Means this nuclei will have maximum binding energy. So this nuclei is representing lowest mass, or maximum binding energy, or maximum binding energy. So this nuclei in this isobaric family, this nuclei which is corresponding to the dip of this parabola, this will represent the lowest mass and it will have the maximum binding energy. So automatically this nuclei will be most stable. So this nuclei will be most stable. So advantage of this mass parabola is, one of the importance of this mass parabola is that we can find out the most stable nuclei with the help of this. Now, what will be the ZA number? A number is fixed. Now, what will be the ZA number of this most stable nuclei? Suppose ZA is the charge number or atomic number of the nuclei which is most stable here. How can we find out the most stable nuclei? It is easy to find out the most stable nuclei. Differentiate this nuclei, this expression. Differentiate this expression of MZA. So now what we will do? Now what we will do, we will differentiate this with respect to z. So differentiate this del m by del z. Differentiate this m for a is equal to constant. For a is equal to constant. So this will be this term, first term will be 0, plus this will be x, it will be 2yz, plus this is dependent only delta. This is delta 1. Delta 1 is equal to delta upon a to the power 3 by 4. So this is dependent on a only. So this will be 0. This will also provide us 0. Now for minima, this will be 0. For minima, we will equate del m by del z equal to 0. So from this equation, we will find out that suppose this is ZA, this is corresponding to this point. So this ZA will come out to be minus x upon 2y. Minus x upon 2y. So the atomic number of the most stable nuclei in an isobaric family, the most stable nuclei will have atomic number equal to minus x upon 2y. Now substitute the expression of x and y. Now substitute the expression of x and y, then what we will get? We will have here ZA. ZA is equal to how much? What is the value of x and y? Substitute here. X is equal to, the minus sign is here, this will be minus 4a minus mn minus mp divided by this will be y. So y will be equal to how much? This will be 4AA divided by A plus AC upon A to the power 1 by 3. AC upon A to the power 1 by 3. So this minus sign will be cancelled out by these minus sign. This will be AA. So this will be 4AA into A. This will be 4AA plus Mn minus Mp. Mn minus Mp divided by this will be 4AA upon A. I can take this 4AA upon A common. I will take this 4AA upon A common. And it will become 1 plus, this will become 1 plus AC upon 4AA, AC upon 4A into A to the power 2 by 3. A to the power 2 by 3. We will have this. We will have this expression. So 2 is here also, this is y, so I have left this 2, so 2 will be here, so it will become 2 here, 2 will be here. Now we can simplify this. How we will simplify? So for this, now we will further simplify this. So this will be ZA. I will further take common 4A is taking common. I'm taking this 4A common in denominator. So this will become 1 plus Mn minus Mp upon 4AA divided by this 4AA upon A is here. This will be 4AA upon A is here. And what I am doing, I will multiply this 2. I will take this 2 inside. So this will become 2 plus AC upon, this will be 2AA upon a to the power 2 by 3. Now this will be cancelled out. This will be cancelled out. And I will have ZA equal to 1 plus Mn minus Mp upon 4AA divided by 2 plus AC upon 2AA a to the power 2 by 3 into A, and this will be equal to ZA. This will be equal to ZA. Okay. Now what we have to do, if we substitute these values, if we substitute all these values here, so this, what are the values nearly? If you substitute all these values here, then you can find out the exact expression in terms of numerical values. You can find out the expressions in terms of numerical values. So I am substituting, or I am writing here the approximate value of this Mn minus Mp is nearly equal to 1.29 MeV upon C square. This is the value of Mn minus Mp, and this value of this other constants are here. This is AA. AA is another constant we have to write down, and this AC is another constant. So values of AA is 24. This is 24 MeV nearly, and AC is 0.75 MeV, 7 MeV. These are the approximate values of these constants. These are the approximate values of these constants here. So if I substitute all these values here, then we will find out that expression of ZA comes out to be, this will be A upon 2 plus 0.015 into a to the power 2 by 3. We will get this approximate formula. 0.015, if you want to write for one more digit, then it will be 0.0154 a to the power 1 by 3. So this is the formula. This is the formula for the most stable nuclei in an isobaric family. In an isobaric family, this is the formula for the most stable nuclei. So in this way, with the help of this parabola, with the help of this mass parabola, we can find out this expression. ZA equal to minus x upon 24. This is for minima. This is for minima corresponding to this. This is the atomic mass, sorry, this is the atomic number of the most stable nuclei. If we further substitute the values of x and y here, we will find out this formula. We will find out this formula. ZA is equal to A upon 2 plus 0.0154 a to the power 2 by 3. Here we have used this constant. Here we have used this constant. So up to this point, we have first find out the mass of the nuclei, and using the V-Shaker formula, we have modified the V-Shaker formula for the nuclei of the mass in the following form. Mass of the nuclei is equal to A times capital A plus X times capital Z plus Y times Z square plus minus delta. If we plot this mass of the nuclei as a function of Z, then we will find out this type of parabola. We will have this type of parabola, and this point, this lowest point of this parabola, this is corresponding to the most stable nuclei. And for the most stable nuclei, to find out the to find out the atomic number of most stable nuclei, what we have done, we have differentiated this mass of the nuclei as a function of Z. So for the most stable nuclei, mass of the nuclei will be lowest. So we have applied the condition of the minima del M by del Z at A equal to constant, it will be equal to 0. When we differentiated this equation with respect to Z and equated it to 0, then we find out the charge number comes out to be ZA is equal to A upon 2 plus 0.0154 A to the power 2 by 3. You have to remember this formula. So basically, to find out this nuclei in a isobaric nuclei, basically in a isobaric family, the most stable nuclei, the Z number of most stable nuclei is given by ZA is equal to A upon 2 plus 0.0154 A to the power 2 by 3. Up to this point, we have find out the Z number of the most stable nuclei. Now we will discuss the case of, basically this is mass parabola for isobaric family. This is not nuclei. This is isobaric family having A equal to odd number. So now if A is equal to odd, now I am considering the case A is equal to odd. Up to this point, we have not considered the odd number or A is odd number or even number. But here if we consider A is equal to odd number, then what will happen? This delta will be 0. So if A is equal to odd, then we will have two type of nuclei. A equal to odd means we can have two type of nuclei, even odd nuclei, or odd even nuclei. So when A number is odd, we can have two type of nuclei, either even odd nuclei or we can have odd even nuclei. In both these cases, this delta will be 0. So in both these cases, this delta will become 0. So when this delta will be 0, so this MZA, this will become equal to A plus XZ plus YZ square. This will be the mass of the nuclei for A equal to odd number. Now, what will be the mass of the most stable nuclei? To find out the mass of the most stable nuclei, this Z will be replaced by ZA. We will replace this Z by ZA. So this is the ZA. This is the mass of most stable nuclei. This is mass of most stable nuclei. So to find out the mass of most stable nuclei, we will replace Z by ZA in this formula. So this will become equal to A into A plus XZA plus YZA square. So this will be the mass of the most stable nuclei. Now, what is the value of X? From here we can find out that X is equal to minus 2Y into ZA. This is the value of X. Substitute this value of X here. So this will become A times A plus minus 2Y ZA into ZA plus YZA square. And this will be equal to AA minus YZA square. Here, the second term will become minus 2YZA square. This is plus YZA square. So we will have AA minus YZ square. Now take the difference of these two. So basically subtract these two equations. First equation for the mass of the nuclei, and this is the mass of the most stable nuclei in an isobaric family. So take the difference of these two, subtract these two equations. What we will have, or what we will find out, when you will subtract these two, then you will find out that MZA minus MZA into A. So this is the difference between these two. I have subtracted the second equation from first one. So this AA, this term will be cancelled out. This term will be cancelled out, and this will become XZ plus YZ square, and this will become minus minus plus, so this will be YZA square. This will become this one. Now again substituted or replace this x by minus 2YZA. So here this will be minus 2YZA into Z plus YZ square plus YZA square. And when we combine all these three terms, we can write all these three terms as YZA minus Z whole square. YZA minus Z whole square, or even you can write it as you wish. You can also write it as Z minus ZA whole square, whatever you want to write down. So here this will be M Z minus A minus M Z A comma A. Here you can write ZA minus Z square, or you can write Z minus ZA square, because Z can be less than A or Z can be greater than A, but because square will give you the same value, numerical value, its numerical value will remain same. So mass of the nuclei MZA, mass of a nuclei can be written as MZA comma A plus YZ minus ZA whole square. So from here you can observe that mass of the nuclei in an isobaric family can be written in this form. And this is a equation of a parabola. This is a equation of a parabola, and this parabola is known as mass parabola. This is known as mass parabola for the isobaric family having A equal to odd number. For A equal to odd number isobaric family, this is the equation of the mass of the nuclei. Mass of the nuclei. So if we plot this, we will find out this type of equation, and this lowest point, its mass will be M. This will be MZA comma A. This will be the mass of the most stable nuclei. Its number will be ZA is equal to minus X upon 2Y, like this. Now we will try to understand the advantage or the significance of this mass parabola with an example. So here I am drawing a mass parabola for isobaric family having A number equal to 73. So I am going to draw here. So I am choosing A equal to 73. So A equal to 73, which is an odd number. Odd number. Now I am drawing the mass parabola for this type of isobaric family. So here on this side we have mass of ZA. Here we have the mass of the nuclei, different nuclei of this isobaric family. On this x-axis we will have Z number, and we will have this type of mass parabola we will have. We will have this type of mass parabola. Now on the z-axis, this point is corresponding to 30. This is corresponding to 32. here we will have 33, or you can say here we will have 34. These are the Z number of different family members. Here this will be 31, this will be 31, and here we will have 30. So these are different, if these are the Z number of different families. Family member will be here. This central member with Z number A, this is 32GE73. This is 32GE. This is 32GE. This 31 is corresponding to GA31, 31GA. This is 31GA. This is 30ZN. This is 30ZN zinc. These are different members of A equal to 73 isobaric family. This will be 33AS. This member will be 33AS. And here last member is 34SC. This is 34SE. And mass number of all these members, members is 73. Is 73. So here this is a isobaric family. Here I have plotted the mass parabola for the isobaric family having A number equal to 73, which is an odd number. So this type of mass parabola is observed for A equal to 73 isobaric family. So here out of these 5 members, this 32GE, this 32GE 73, this will be the most stable nuclei. This will be most stable nuclei. Most stable nuclei. Because this is corresponding to the dip. Because this is corresponding to the dip of this mass parabola, or mass of this nuclei, mass of this 32GE73 nuclei is the lowest, has the lowest value basically. Now, this is the most stable nuclei. These are less stable nuclei. Other 4 nuclei are less stable. Now they want to achieve the stable configuration, stable nuclear configuration. So this 30ZN, 31GA73, these are all 73 nuclei. Here these are all 7. So basically these 4 nuclei are unstable nuclei, and they want to find out this stable nuclear configuration given by 32G. So this 30ZN73, it want to convert into 32GE. So how can it convert? If you observe this 30ZN73, if you consider this 30ZN73, then in 30ZN73, basically number of neutrons, here number of neutrons is higher as compared to number of protons. So here number of neutron is equal to how much? This will be 43, and number of proton is 30. Here in 32GE, in case of 32GE73, number of neutron is 41, while number of proton is 32. So here, as compared to this stable nuclei, this 30ZN73 has higher value of neutron. This nuclei has higher number of neutron, not value, higher number of neutron. So basically, to achieve or to convert itself into this stable configuration, what it has to do, it has to convert one of its neutron into the proton. So one of the neutron can convert into the proton. So basically what is the process by which it can reduce its number of neutron? So neutron can convert into proton. Neutron can convert into proton, and a beta minus particle will be emitted, and along this beta particle there will be a neutrino. There will be a neutrino particle, anti-neutrino particle that is also emitted in this process. So basically this 30Zn73, it can move towards the more stable configuration. It can move towards the more stable configuration 32GE if it converts its neutron into a proton by emitting this beta minus particle. So what will happen here? This 30Zn73, this will emit a beta particle, beta minus particle, and it will convert 31Ga73. So basically if number of neutrons are higher as compared to proton with respect to stable configuration, then neutron will convert into the proton inside the nuclei and beta minus particle will be emitted. So this 30Zn73, this will emit a beta minus particle. Here this will emit beta minus particle, and this 30Zn will convert into 31Ga. Now this 31Ga is again unstable with respect to this 32Ge. So again one more neutron will convert into proton and it will again emit beta minus. This 31Ga73, it will emit a beta minus particle and it will convert into 32. This will convert into 32Ge73. So if number of if number of neutrons are higher as compared to number of proton, and with what reference? With the reference of this most stable nuclei, then neutrons will convert into proton, beta minus particle will emit, and these nuclei, this and this nuclei, they will achieve the stable nuclear configuration by emitting beta minus particle. Or you can generalize it. If you have a nuclei in a isobaric family, if you have a nuclei which is to the left of this most stable nuclei, then by emitting beta minus particle, they can achieve the most stable nuclear configuration. Now come to this case here. Now consider this one, this 34SC73 and this 32Ge. So this 32Ge73, if you consider here, then number of proton is 32 and number of neutron is 41. This is the number of the proton and neutron in the most stable nuclei. And if with respect to this, I consider this 34SC73, then here number of proton is 34 and number of neutron is 39. It is 39. So with respect to this most stable nuclei, you can observe that number of neutron is higher here as compared to this, number of proton is higher. So if this nuclei want to convert itself into the most stable nuclei, then proton has to convert into neutron. Then it has to convert one of its proton into neutron, and in this process beta plus particle will be emitted and it will be associated with a neutrino. So if a nuclei which is on the right hand side of the stable nuclei, it want to achieve the stable configuration, then it will emit beta plus particle. How? So basically this process will be like this. This 34SC73, this will emit a beta plus particle. And by emitting this beta plus particle, it will convert into 33As73. This 33As73, it also has number of protons higher as compared to the stable nuclei. then again it will emit beta plus particle, and it will convert into the most stable nuclei of this isobaric family. So on the basis of this type of analysis, we can predict that one of the nuclei in an isobaric family, either it will emit beta plus particle or beta minus particle. So what is the rule for this? How you will find out? Suppose I am giving you 73, isobaric family with 73, then using the formula for the most stable nuclei, first you will calculate the ZA. Then first, using the formula for ZA equal to A upon 2 plus 0.0154 A to the power 2 by 3. First, I will find out the most stable ZA number, this charge number or atomic number for the most stable nuclei. First, I will find out. And then I can predict if a nuclei whose Z number is less than ZA. If in the isobaric family we have a nuclei which has Z number less than ZA, if Z is less than ZA in a isobaric family, then this will emit beta minus particle. Then beta minus emission will take place. To convert itself, basically this nuclei with Z number less than ZA in an isobaric family, then it will prefer beta minus emission so that it can achieve the most stable configuration. If Z number is higher, if the Z number is higher as compared to ZA, then it will emit beta plus emission to achieve the most stable nuclear configuration in the isobaric family. So in this way we can decide in an isobaric family that either it will emit beta plus particle or it will emit beta minus particle in an isobaric family. Now we, on the basis of this formula or with the help of this formula, we can also find out the Q values during the emission of beta minus particle or beta plus particle. Suppose, so I'm not removing this here. This formula, I'm going to use this formula, and on the basis of this formula, I'm going to find out the Q value during the emission of beta minus particle. So what will be the Q value? Q value during the beta minus emission. So we have to find out the formula for the beta Q value of the process during the beta minus emission in an isobaric family. So I'm writing this formula here, mZA. This will be equal to M mass of most stable nuclei ZAA plus Y times Z minus ZA whole square. So we are going to use this for suppose the beta minus emission process is ZXA. This is the unstable nuclei. This is emitting beta minus particle, and it is converting into Z plus 1 XA. So here this beta minus particle will be emitted, and this will be antineutrino here. So this is the journal. This will be Y. This will be another nuclei because its charge number is Z plus 1. So this is the journal beta minus emission process. Here A number is same. So both X and Y, they are the members of the same isobaric family. Now what will be the Q value? What will be the Q value here? Q value will be equal to mass of parent nuclei, mass of ZA, mass of this parent nuclei minus mass of the daughter nuclei, this Z plus 1 Z plus 1 comma A, comma mass of beta minus particle minus mass of antineutrino particle. Here, mass of beta, they are negligible. Here, basically mass of this beta minus particle and mass of antineutrino is negligible. These two values are negligible. Negligible as compared to these two values. So basically our formula will become, if we neglect these two masses, then and multiply this and multiply this. So basically this will be equal to this one. So substitute here. Substitute these two, m beta minus and m antineutrino, these are negligible. So this Q value will be mZa minus mZ plus 1 into A. Z plus 1 into A. So this will be the Q value. Now substitute. Now substitute the value of mZa from here. So this will be mass of ZA, comma A plus Y Z minus ZA whole square minus mass of this nuclei. Here this will be mass of ZA, comma A, mass of the most stable nuclei plus Y times, here in this formula we will replace Z plus 1, this Z will be replaced by Z plus 1. So this will become Z plus 1 minus ZA whole square, and like this. This will be the formula. Now, this mass of the most stable nuclei will be cancelled out by this, and here in these two terms this Y will be common. Open this square, so this will become Z square plus ZA square minus 2 times ZA, and here minus sign is here. Y is common here, we have already taken this common. Now square of this term, so this will become Z square minus 1 minus ZA square. This will be Z dot 1, Z into 1 into 2 times, so this will be 2Z with minus sign, so this will be minus 2Z. This 1 into minus ZA, so this minus minus will become plus, this will be 2 times ZA, and if we consider these two terms, again this will become 2 times ZA. So we will have this value. Now this minus 2ZA, this will be cancelled out, this will be cancelled out. This ZA square, this ZA square will be cancelled out, this Z square will be cancelled out, and what we will have, we will have this term, and this one. So we can write it as Y times 2ZA minus 2Z, and this will be minus 1. And if I take this 2 common, this will become 2Y, and here you will have ZA minus Z minus 1 by 2. So this is the Q value for beta minus process. Here Q value is this. For this beta minus emission process, this is the formula. This is the formula for Q value. Here you have to remember one thing, because Q has the unit or dimension of energy, so this Y, this constant Y, this will also be in terms of energy. It will also have the dimensions of energy. So always substitute this Y in terms of dimension of energy. This Q already has dimension of energy. So this will be the formula for Q beta minus. So in this way we have find out the Q value of beta minus process for any arbitrary beta minus emission process. Now in a similar way, we can find out the Q value of beta plus emission. We can also find out the Q value for beta plus emission. So for this, what will be the equation? For this equation will be Z minus 1, this will be Z plus. So this is the general equation for beta minus emission. Now we will find out the Q value for this process. Now we will write down, or we will find out the Q value of this beta plus emission. So what will be the Q value for this beta plus emission? This will be equal to mass of parent nuclei Z, A minus mass of daughter nuclei Z minus 1, A, and here we will have two terms with minus sign, mass of beta plus and mass of neutrino, but mass of electron, this positron, and mass of neutrino is negligible as compared to these terms, so we are neglecting the masses of beta plus and neutrino. So this will be the formula for Q beta plus. Now substitute value of MZA here, so this will become MZA, A plus Y Z minus ZA whole square. This is the value of this mass of ZA nuclei. This is the mass of ZA nuclei with minus sign here, minus sign. Mass of this nuclei having Z value as Z minus 1. So use this formula, it will become MZA, A minus, or this will be plus here, plus Y, and here this Z will be replaced by Z minus 1, so this will be Z minus 1 minus ZA, and this will be whole square like this. This will be whole square. So this term will cancel out by this term, and here Y will be common. Y will be common, and this will become Z square plus ZA square minus 2 times ZZA. Now open this square, so this will be minus Z square minus 1 minus ZA square, and this will be this into this, so this will be minus minus plus 2 times Z. This and this will become again this will become plus 2 times ZZA, and this will be minus minus plus 1 into ZA into 2, so this will become minus 2 times ZA. So here this Z square will be cancelled out, ZA square will be cancelled out, this will be cancelled out, this term will be cancelled out. Only 3 terms will survive, and we will write these 3 terms as we will write it as minus 2 times ZA, minus 2 times ZA plus 2Z, and this will be minus 1. If I take this 2 common, then this will be Y, and here I will write here 2. This will become with minus sign ZA minus Z minus 1 by 2. So this is Q beta minus. What is the formula for Q beta minus? Q beta minus, this is equal to 2Y minus ZA minus Z minus 1 by 2. This is the formula for Q beta minus. Q value of beta minus emission process in an isobaric family. In a isobaric family, we can combine these two formulas together. So sorry, this is beta plus. Sorry, this is beta plus. So we can combine these two formulas. We can combine these two formulas, and we can write these formulas as Q beta minus plus. So we are combining these three, minus plus. This will be equal to 2Y. With minus, here we have plus, and with plus we have minus here. So first I will write plus, then I will write minus. This will be ZA minus Z, and minus half. This is the Q value of beta emission process. This is the Q value of beta plus minus emission process or beta emission process. So in this way we have find out the most stable nuclei and then we find out, or basically we have discussed the mass parabola for isobaric family having a number which is equal to odd number, having a number equal to odd. For example, then we have taken an example of A equal to 73 isobaric family. I discussed the mass parabola, and on the basis of mass parabola, we have find out that all the members of this isobaric family which has Z less than ZA, they will emit beta minus emission process. They will emit beta minus particle to achieve this most stable nuclear configuration. And all the nuclei, all the members of this isobaric family which are on the right hand side of this ZA nuclei, most stable nuclei, they will emit beta plus particle to achieve the stable configuration. After this, we have find out the Q values of beta plus emission process and beta minus emission process.